Okay, so last time I think we stopped here, around here. We were talking about power flow. I started introducing power flow, and I was saying basically power flow is, it's a fancy term for just solving the circuit, right? So the reason we spend time on it is really solving the circuit when you are not given the voltages, for example, is not something we know how to do, right? So in 214, for example, you're typically given your voltages and you have your impedances. You find your equivalent impedances and series, parallel combination, star, delta conversions, whatever you want to do, and then you divide voltage by current by impedance, and you have your currents, right? Then you can sort of go back and redistribute your circuit here. But in power systems, we are typically not given voltages everywhere in the circuit here. We are typically given powers. So I'm typically told that the power that this load is going to consume is approximately so and so. The power that this load is going to consume is probably so and so, right? So there's it's a sort of a different way of dealing with an electrical circuit. So one way, so the if you would like a simplistic way of what we're gonna of looking at what we're gonna do is, if you have your power equation, your powers are given, so that means you have your P plus JQ on one side. P plus JQ is also equal to V times I conjugate, right? That's the complex power, right? So writing it in rectangular form and writing it in polar in complex form, right? Writing at P, you can write power, sorry, complex power. You can express it as P plus JQ or V times I conjugate, right? So if you are given, for example, P and Q, right? And then you are given some V's and maybe some I's, for example. One way to go about this is maybe plug in estimates for the rest of the variables, that you don't know, right? And see if both sides become equal, right? So that's sort of the approach that we're going to use, So it's we're going to have unknowns, and we're going to assume what they are, given some using some proper engineering judgment, and then we're going to sort of iterate until we sort of match the difference between what's on the left-hand side of the equation versus the right-hand side. So P plus JQ, which is something we know at the bus. We know that every bus, for example, I have a generator. It's going to be producing a certain amount of power. I have some loads. They will be consuming certain amounts of power, right? So I sort of know this P plus JQ in many places, right? And the other side of the equation, I will sort of guess some variables in this other side of the equation and see if they're equal. If they're not equal, that means my guesses were wrong. And I need to find a better way to estimate my guess, right? And that's the iterative solution that we're gonna learn in this chapter, right? So it's a typical numerical method that is taught in any numerical analysis class, right? So if you take any numerical methods class, you will learn one of the methods that we're going to talk about in class in this chapter. So last time we were talking about this circuit here, and I was saying, okay, if I would like to find the currents in these branches, right? The currents in these branches are equal to basically the voltages at the two nodes that are at the terminals of each branch, divided by the impedance, or multiplied by the admittance, right? But the problem we posed last time was I can increase voltage at node 1, voltage at node 3, right? Together by 10 volts. And the difference will still be the same. So if I divide that difference by the impedance, I'll still get the same current in the branch, right? So it's not clear what needs to be done in this case. So what we do, and I'll show the effect of, and I showed the effect of that in the matrix, right? So we came up with the matrix that defines this circuit. So the matrix that defines this circuit, so we did Kirchhoff's current law at the different nodes. So at node 1, the I1 is coming in, I12 is coming out, I31 is coming in. So that's Kirchhoff current law at node 1, Kirchhoff current law at node 2, Kirchhoff current law at node 3, right? Each of these currents is equal to the voltage difference divided by the impedance, or multiplied by the admittance, right? So Kirchhoff current law here. Everybody's okay with this? Yeah. So each of these currents, I will express it in terms of the admittances and the voltages. So I will rewrite, for example, I12 as what? I12 is equal to the voltage between these two nodes, V1 minus V2, divided by JX12, or multiplied by Y12, admittance of this branch, right? So V1 minus V2 over JX12, and I do the same for everything, all of them, right? And I'm gonna be able to, write my. I would like to put this in matrix form, the same matrix that we came up with or derived last time, where I have currents on one side, voltages on one side, and the link between the voltages and currents, the admittances or the impedances of the circuit. Yeah, right. So that's what we did last time. So I will, factor out V1, factor out V2, and rewrite the equation in the three equations in this fashion, and write the matrix. So last class we wrote up this matrix. We derived this matrix in the last class. So I think I'm not going to spend more time doing that. And what we stopped at, where we stopped was, we said that if I add these three together, if I add all the rows together, the sum is 0. Right? So here, if I would like to find the voltages, what do I need to do? I need to invert this matrix and pre-multiply it by the currents. Right? If I'm given the currents, for example, and I would like to find the voltages, I would need to invert this matrix. For me to invert this matrix, it has to be a non-singular matrix, right? For it to be a non-singular matrix, the rows of the matrix need to be linearly independent, right? So here, if you add all the rows, the sum is 0, right? So these equations are linearly dependent, right? So mathematically, there's some problem with being able to solve this circuit using these three equations here. So what we do in power systems, as one simplistic way of looking at this, is what we will do in a big power system, which is we will assume that one of the voltages is known. If you assume one of the voltages is known, right, then you can sort of eliminate one row and one column. You will end up with a 2 by 2 matrix, right? If you know V3, for example, then you can eliminate this row and you can eliminate this column. Everything with a 3 you can eliminate. Right, so then you will have a 2 by 2 matrix. Add these two up, and then you will not have a problem. The matrix will be linearly independent, and you can invert it here. That's sort of what we need to do mathematically. Okay. Does this have a physical interpretation or physical meaning? Yes. Okay. So mathematically, this is some math that is not very physical, not very interesting here. But in a power system, we actually have something very similar to this happening here. So we have different kinds of buses, and we'll talk about those. So let's remember this mathematical sort of tool that we just said. Okay, trick. Okay, cancel. Okay, I know one voltage. I will have one guy sit and measure the voltage instead of covering the generator. Measure the voltage there and tell me, okay, this is my voltage. So then I can solve my system, right? So that's sort of what I'm saying for now. Yeah. And and then we also introduced the term admittance matrix in the last class. We said that this is called, this Y matrix, the admittance matrix here is called, sometimes it's called the Y bus matrix, or it's called the admittance matrix. And it's composed of, its diagonal elements are the sum of admittances connected to each bus. So this is a 3-node system or a 3-bus system, right? And at every bus, there are several admittances connected, right? So this is JX31, JX12, right? So Y11, the admittance matrix element 11, will be the sum of all elements connected to bus 1. Y22 will be the sum of all admittances connected to bus 2. Y33 will be all admittances connected to bus 3, right? So if you go to down here, you will see Y12 plus Y31 is Y11. Y11 is Y12 plus Y31. So the admittance is connected to bus 1. Yes, sir.
Are these admittances imaginary or complex?
It's the same. I mean, it's we forgot about the resistor here, but that doesn't mean that's always this case. Sometimes we will consider resistance here, right? So sometimes, I mean, this is only the imaginary component here, which is only the reactance, but in certain cases we will consider. So there's an example here later on. We will consider both. When we derive the equation to solve the full system, we will consider both, yeah, resistances and inductances present, yeah. Okay, but instead of, if you have a 10,000 node system, right, you want a way to come up with this matrix. You don't want to have to write Kirchhoff current law at every node, simplify the equations and do this, right? We want a way to do this very quickly so we can computerize it, right? That's the objective here. So we construct the Y-bus matrix like that. So the diagonal elements are the sum of the impedances. The off-diagonal elements are the negative of the impedances between the two specific buses. So element Y12 in the admittance matrix will be the negative of the admittances connected between bus 1 and bus 2. Right? So Y12 is the negative of the admittance connected between bus 1 and bus 2. So on and so forth. These three are like that. And then the matrix is also symmetric. So the Y12 is equal to Y21 element of the admittance matrix. So if you get the top half, you just copy the bottom half. Okay, so that's how you check if your work is right or wrong. Right? So you can quickly construct this Y-bus matrix. The admittance matrix can quickly be constructed. And the order of the admittance matrix is the order of your system nodes. Right? If it's a 3-bus system, it's a 3x3 matrix. We'll have many matrices in this chapter, right? So, and each of them will have a different order. So that's why it's important to know the order of each of these matrices. Yeah. So this would be the order of this would be the order of the system buses. Yeah. Okay. So it can be seen that the bus admittance matrix is n by n because you have n number of buses, and each diagonal element, which is the self admittance, equals the sum of the admittances connected to the specific node. And the off-diagonal elements, ykn equals ynk, which means that the matrix is symmetric, and these are the mutual admittances, and they are equal to the negative of the admittance connected between nodes k and n. Right? That's what we just said. And we talked about this idea of inverting the matrix. And we also mentioned that in our case, in the power flow problem, we don't have voltages and then to calculate the current just by multiplying by the impedance matrix. We're given powers. And we saw the anomaly in the math as well. Okay, so we'll see how we deal with that. Actually, I mentioned how we can deal with it mathematically, but I want to see. Let's see if we can have a physical representation of that as well. Yeah. So the power flow problem. The power flow problem assumes, of course, that you have a balanced system, right? And it's operating in steady state. So this is not a transient solution for the system. We are not going to look at a certain harmonic content or the power quality of a waveform. We're not going to look at that, right? We are looking at steady state solution of your circuit here. It's like the AC steady state analysis in 214, right? That's basically what we're looking at here. Yeah. So, and it's typically done using computers, of course, and PowerFlow is an example of a method of software that does load flow or power flow analysis. And I think just to give you the bulk of the power flow problem is really collecting the data. Actually, the bulk of a power system simulation or assessment or study is collecting the right data. Like if you want to really understand your power system and simulate it, you have to spend a lot of time collecting data. Doing the simulation itself is afterwards very easy, and we will see a sample of what sort of data we need to collect for a power system. So we will define 4 variables. So at the specific bus, if I would know the voltage and angle as a magnitude and angle, and a voltage as a magnitude and angle at every bus, then I can figure out what the power flows are, right? So definitely the voltage, magnitude, and angle are 2 of the variables that are important for me in this power flow problem, right? The other 2 variables that are important for me are the real and reactive power, right? Because again, in electrical engineering, I have equations of I have 2 equations: equation Ohm's law, and I have the complex power equation. I have V equals I times Z, or I can write that in the admittance form, and the other equation is S equals V times I conjugate. Right? These are really the two equations that I have to play with here. So the impedances, they should be known. Right? The impedance will be known. So what I will need to play with are then the voltages and angles and active and reactive powers. If I have voltages and angles and active and reactive powers, I can do this inequality that I was talking about. I will write it down later there. But this inequality of equating, for example, complex power using an expression that includes voltages and angles and impedances and the real and reactive power on one side. So how are we going to go about this? So the first step in constructing or starting the power flow problem is looking at every bus. So this is one bus, for example, in your power system. So you look at every bus and you find out what are the specified or the net real and reactive powers. So the net real and reactive powers are PK and QK at every bus. So I would like to go to every bus because if you have a generator connected to that bus, this generator will be supplying a certain amount of power, right? And it will be delivering that power at a certain voltage, for example, right? But will you know what that generator will supply from a reactive power perspective, or is there you specify that or do you just have a limit or a constraint on that? You would like to deliver as much real power as possible, right? And you would like to deliver that as much real power as possible at a certain voltage, right? So that's sort of how the generator likes to function, right? It likes to sell real power, and it likes to be rated for a certain voltage, right? So for generators, typically the variables that we will know are real power and voltage. We will not know, for example, the angle of the voltage, though. It doesn't matter for the generator. From a generator's perspective, physically, I don't care if I'm synchronized with this generator or that generator, right? For a generator, when you buy it or when you specify it, you will typically be concerned about how much real power it has to supply and the voltage level, right? The system will define how much reactive power is drawn. Of course, there's going to be a limit on the generator's capability to deliver reactive power because, again, a generator is rated for a certain amount of apparent power, right? Any AC equipment is rated for a certain amount of AC apparent power. This apparent power, how much do you want to sell the real power? You're forced to supply some reactive power based on how the system is designed, right? So the generators will be supplying real power, and they will supply that at a certain voltage. So these will be the known values from a generator's perspective. How it's synchronized to which generator, that's going to be an unknown. So the angle will be typically unknown, and the reactive power will be typically unknown that will be drawn from the generator, right? So now out of the four variables that at the generator, but if a bus has only a generator, then I know two, which are the P, real power, and the V, and I don't know angle, I don't know reactive power because these will depend on the system, right? If at that bus I have a load, a motor, you're specifying this motor based on what? Okay, this process needs to run a compressor. This compressor is rated for a certain amount of power, right? You need to deliver a certain amount of power. You're going to supply that with an induction motor that has a power factor of so and so, which means you know P and Q for a load. You don't know yet what voltage level it needs to be connected at. We don't care. The chemical engineer is specifying the process. The process consumes a certain amount of power. Did they tell you, I need it to be run at 10 volts? No. You're going to design the electrical equipment or specify that or buy that to plug it into your system. So at a load bus, you will know P and Q, right? And then the unknowns in that case will be the voltage as a magnitude and an angle. So this is now the generator bus and the load bus. In a power system, you typically also have a generator that's going to be a reference generator. So you will have a generator that is not going to be limited by, when you run a generator, you have a country that is going to be requiring a certain amount of power. So the utility actually dispatches a certain amount of power based on the requirement. So it will tell all the power producers, guys, we have this much power in Qatar, base load, right? Fine, there are variations throughout the day, but I need a certain base load power of a certain amount. For example, this building has a certain base load power of about 1.4 megawatts. About 1.4 megawatts, pretty much consistent throughout the day, throughout the night, throughout the summer, throughout the winter. But then when people come in the morning, there's a higher load on the AC, higher load on the lighting. So we have some higher peaks during the day and maybe some higher peaks during the night if we have an event, etc., etc., right? But there's a certain base load that needs to be supplied. So this base load and the other load has to be dispatched by the utility. Kahraman has to be able to make sure that this power is available. So there are certain power stations, for example, like the Ras Abu Funtas power stations, the big combined cycle power plants, that will be providing this base load, and they will not really change their power throughout the day. And that's what we were talking about from from a perspective of at the generator bus, or from a utility perspective, at a generating power station would typically have a certain power limit it continuously provides, right? That's why I said if a bus has a generator at it, I typically know my real power capability and my voltage, because this power plant, I cannot just shut it down, right? I mean, you cannot just turn on a power plant and shut it down, right? So especially these large combined cycle power plants, or these steam power plants, or coal-based power plants, or a nuclear power plant, you cannot turn them on and then turn them off, right? These are power plants that require a lot of time to turn on, and it costs money to turn these things on and keep them running. So it's you have to these power plants have to have contracts with the utility saying, okay, you guys will take a certain amount of power from me every single day, every day throughout the year, right? So for them to be able to make sure that the economics make sense, right? So these guys, these big power plants, will provide these constant power at a certain voltage. How about these fluctuations in power? In the first class that we had, I remember saying that we have these some of the power plants that these large combined cycle power plants that produce power and water that need to be really running continuously, really are located around on the shores, on the beach, right? So that they can desalinate the water as well, and they are very large power plants that you cannot just shut down, right? I also said that there are some smaller power plants inland. There are a few smaller power plants inland, and if you go to Kahraman's website, you can see the various power plants in the country. But there are a few power plants that are inland, and these are gas turbine based, right? It's like a machine, so it's a gas turbine. You run the gas turbine, it produces power, almost instantaneously. You buy it, you buy the gas turbine, you plug it in the system, it runs, right? These gas turbine power plants are the ones that accept this changing load and provide this changing load throughout the system, right? They are the ones that respond very quickly. So they respond very quickly, that you can turn them on, you can turn them off a lot quicker than these large combined cycle power plants. So these power plants are not providing continuous power, right? Because I just said that they're providing these changing power. So for these power plants, I actually don't know P. And I also don't know Q, because Q depends on what? The system, right? I have inductors, I have loads, I have resistors, I have power factor correction, I don't have, right? So there will be a bus, or buses sometimes in a power system, where with a generator on it, that I know its voltage as a magnitude and an angle. And I will use that as a reference, right? And that's sort of the mathematical anomaly that we also dealt with in the inversion of the matrix, right? In inverting this matrix, I said it's singular, but if I know a certain voltage as a magnitude or an angle, I've solved it, right? And we actually have that physically happening. We typically have a power plant, typically gas turbine based, that will be acting like this reference power plant that I have. It will be providing fixed voltage, but fluctuating power, right? So I will know, and I will use it typically as my reference. So angles will be measured with respect to that power plant as well. So remember, I don't care about absolute values of angles, because two people moving together. Do I care about their absolute measurement with respect to the wall, or do I just care about how close they are together so that they can hold hands, right? I just care about if they're close together or not. My objective is to have them hold hands. I don't care if they're close to the wall or not, right? So it's like the generator, right? So I just want to make sure that the angle differences are controlled. I am controlling the angle differences in the power system, right? So having a reference is a good thing. So instead of talking about angle differences, we will be talking about an angle with respect to a reference. And if we make that reference, we call that reference 0. Does it matter? It does not matter. I will call this 0. And everything here is 1, 2, and 3, right? So I will at these buses with these generators that will be providing this fluctuating power, I will sort of use them as a reference for voltage and angle, right? And these buses will be called slack buses or swing buses. Swing meaning they swing the power, right? So that they're called slack or swing buses. So you will typically have these one or more slack or swing buses in the system, and that is what you actually need to solve the equations. But this is actually physically present as well, right? So we talked about three kinds of buses now. Which ones did we talk about? Yeah, so PQ, PV, and slack, right? So we have three types of buses. There's nothing else, right? Sometimes you have a generator and load on the same bus, but in these cases you will sort of take the sum. You look at the bus, all the power at the bus, generation and load, and of course if generation power is greater than the load power, then it's also a PV bus. It's a generator bus, right? So if the load power is more, then it's a load bus, right? So we just have these three buses. So at every bus, you need to go and look at the specific power at the bus, PK. And it's going to be the difference between whatever's generated and whatever load power is at that bus. And that will be your P and Q at that specific bus, right? You equate that P and Q with your equation for complex power, right? Your equation complex power is S equals V times I conjugate, right? V times I conjugate, we can sort of, if I have V, for example, and I solve for I's, I take I equals this admittance matrix times V, and I have what? Then I have P and Q on one side, right? And then S equals V times I conjugate, so I have V, and so on the right-hand side, I have a bunch of voltages and admittances, right? And these voltages have magnitudes and angles, right? So now I have a bunch of voltages and admittances on the right-hand side, and I have a bunch of P's and Q's on the left-hand side. So I have, at every bus, I have an equation for real power. So let me just look at the equations. So yeah, we talked about the different buses, right? So we mentioned the swing or slack bus, load or PQ bus, and the voltage or PV bus, right? And we said that at a slack bus, I know voltage as a magnitude and angle, and so the unknowns would be the real and reactive power. At a generator bus or a PV bus, I know P as a real power, and I know voltage as a magnitude. And then what I don't know then out of the four variables are the reactive power and the angle. And then for a load bus, I know P and Q, and I don't know the voltage and angle, right? So these are the three types of bus that we have. So, and then the next step, of course, is going to be to form the admittance matrix, which we formed for a small system. And this, I will go through this slide to show you, to talk a little bit about how we represent the other components in the system. Yeah. But basically, it's form the admittance matrix. So here they say that to form the admittance matrix, you have to make sure, this is for a balanced system, and the balanced system means that the system can be represented by a single-phase positive sequence network using lumped impedances, which is what we've been doing. We said that the transformer, let me skip this point and come back to it. So transformers will be represented using their equivalent circuits. So we came up with a few equivalent circuits, either with the phase shift considered or without the phase shift considered, and basically it was a series impedance. For transformers, we had a series impedance, and then if we had no phase shift, star delta, the only thing was the series impedance. If we considered the phase shift, then it was a series impedance with an ideal transformer with a certain phase shift, right? That was the model in per unit, right? We didn't talk about, three-winding transformer models or tap changing transformer. They are just another model, okay, similar to this series impedance with an ideal transformer, right? I don't care. We're not going to cover them, right? They're just another equivalent circuit model for a transformer, right? And then the transmission line, we talked about that last class. We said that the transmission line, the single phase equivalent circuit representation for the transmission line will be what? We represent that transmission lines using their pi equivalent network, right? Do you remember that? So this is the one point of the transmission line, one end of the transmission line. This is R, this is JX, and then this is JB over 2, JB over 2, where this is the susceptance divided by 2. Susceptance is the inverse of basically the complex component of the admittance, of the impedance, yeah. So this capacitance represents the voltage difference, basically, that you have a transmission line with a certain voltage level across it, and then you have ground or earth, right? So there's, it's like sort of two conductors with opposite charge across them with a dielectric between them. So it's represented as a capacitor, right? So we will go and derive this go back and derive this after this chapter, but I prefer to do the power flow chapter first and then go back, because again, this is nothing but another equivalent circuit for a transformer. Our equivalent circuit was, so this is our equivalent circuit for the transmission line. This is the equivalent circuit for the transformer, or if it has the phase shift, we consider phase shift, we put this, right? For a load, the equivalent circuit is nothing but some load, right? For a generator, it's a voltage source, right? So I have generators, I have loads, I have transmission line, I have transformers. I don't have anything else in my power system, right? So and all of these are what? All of these are represented either by, all of these are represented by the, I either have the impedance or I either have the voltage value, right? Nothing else. So now if I want to construct my Y bus matrix, my admittance matrix, we said that admittance matrix, the order of the admittance matrix is the same as the order of the number of nodes that you have in your system. And then the diagonal elements are the sum of all the admittances connected to a certain bus. The off-diagonal elements are the negative values of the admittances connected between two specific buses. That's it. So that's what this slide says. We'll do an example and this is what it says. Okay. So after you've sort of gone through and identified what buses do you have in the system, so you've done this, looked at the total power at the bus, identified the different buses that you have in the power system, either swing, load, or peak, or a PV bus or a generator bus. You then construct your admittance matrix. Right? This is the step-by-step procedure to solving the power flow problem. After you solve your admittance matrix, now you can play with your equations. You know that if you go back to the equation, the matrix that we constructed, and you look at I1. I1 is equal to, admittance is connected between bus 1 and admittance is connected at bus 1 multiplied by the voltage, plus the admittance connected between bus 1 and 2 multiplied by a certain voltage, plus a certain admittance multiplied by voltage V3, right? So we wrote these equations based on just nodal analysis, correct? So I can write this using a summation, and I can write this, instead of this way, I can write this as a summation where, for example, I have something that represents admittance from the admittance matrix. So I sort of have a I1 is equal to a summation of y xy multiplied by vn, for example, right? So I can have n go from 1 to 3, so I can cover the different voltages, V1, V2, and V3, and I have something that represents elements of this admittance matrix that is basically that I can take and plug into this equation. Right? I can rewrite this in that fashion. So if I look at what I have here, I can write the current at a specific bus as a summation of some impedances multiplied by some voltages, which is basically the nodal equation that I have. I rewrote it in this format. So this is I. I know that I have certain powers and real and reactive powers at every specific bus that I looked at. So I went, remember the first step was to go to every bus and calculate PK and QK at the bus. PK and QK were the sigma powers at that specific bus, right? So I know sigma power at a specific bus, P and Q. And then I know that that is equal to the complex power. I have an expression for IK in this format, in summation format, based on my nodal analysis, right? So I can take IK from here, I can take IK from here and substitute it in here, right? I will take this summation here and I will substitute it here. So I will keep VK outside, VK stays outside, and then I will take the summation and conjugate it, okay? So I know that all the voltages are complex quantities, and the impedances are complex quantities as well, right? So I can write the voltages and impedances in this way. The voltage at a specific bus, Vn, is equal to Vn as a magnitude, e to the j delta n. So that is the angle of the specific voltage, and n is Vn is the magnitude for bus voltage for bus n. I can do the same for the admittance between two buses, or the admittance from my admittance matrix, right? Every element in the admittance matrix is a complex number that can be written as ykn is equal to e to the j theta kn. And then this can, of course, be written in rectangular form. So now I can take these two, I can take the voltage and admittance, the voltages and admittances, and plug them back into here, and write all the voltages and admittances in complex form. So consider all the angles that we have, right? So the left-hand side is the same, right? The left-hand side does not change, right? Left-hand side is exactly the summation of P and Q at every bus, right? A specific bus K for this example, right? At each bus K, I have already found my PQ and PK and QK. And then I go back and substitute, expand this further. So VK is equal to what? VK is equal to a magnitude VK, e to the j delta k, right? The VK is constant, it's outside. It is multiplied, it's common. I'm finding the bus at this voltage here. I'm finding the voltage at this specific bus. If this one here stayed outside, right? It's outside the summation. VK here is outside the summation, right? This comes from the complex power equation, right? So my complex power equation has a VK here. This VK is going to be common, right? So it stays outside. It stays outside here. And is a magnitude, and this is its magnitude only. But this is a complex number that has an angle as well. So it's equal to e to the j delta k. So I will bring the e to the j delta k inside. Okay, and then because I have to multiply the angles will you have to, if you're complex numbers, for you multiply them, you have to add angles, divide them, subtract angles. So that's what I'm doing. I have a complex number, magnitude and angle. I'm keeping the magnitude outside, and I'm bringing the angle for that inside. And then ykn is inside the summation, and its angle is theta kn. The angle is theta kn. It's negative because of the conjugate, right? No. Why is it? No, this is wrong. The conjugate is wrong. It's negative because of the conjugate.
So it is negative because of the conjugate, because up there the end is.
Yeah, but they still kept we still kept the conjugate here. That's what I'm saying. So this thing here is, you should remove this. Sorry, this has to be removed, yeah, because remember, because look here, we keep it and we don't have the conjugate anymore. Okay, so this conjugate here is a typo. Okay, so it's YKN, and we change the angles of the impedance to a negative, and the angle of the voltage to a negative value because of the conjugate that we have. So this conjugate is a typo. Okay, and now I have this equation, and I can expand it. I can write it. I can write the real part alone and the reactive and the imaginary part alone. And of course, and this is another typo. Sorry, this has to be Q. Okay, so this is Q. You will have the power flow equations in your equation sheet, and they're correct. Yeah. So I have this equation now, and then I split it up into real and imaginary parts, and I rewrote it in this fashion. Or I can, and this is in polar form. I kept the impedance in polar form as a magnitude and an angle, right? I can also write it in rectangular form as conductance and susceptance, right? G plus JB, right? So this is, you can write the power flow equations at every bus in either in polar form or rectangular form, and you will have those available for you in your equation sheet. So what we've done is the following. We started off with our real and reactive power equation known at every bus. So I went to every bus here. Yeah. I went around every bus in my system, and I looked at the sum of powers coming in and sum of powers coming out of the bus. So generating power is coming into the bus, meaning it's positive. Load powers are coming out of the bus, or they're negative. So at every bus, I know my PK and QK, right? That's what I have at every bus. And then I go back and use my and then the next step is identify the types of buses that you have in your system. Why we'll do that, I will come to that very shortly. Because we have 4 variables, at every bus I need to know which variables I have and which variables I'm looking for. Remember, I have PK and QK at every bus where it's possible to find PK and QK. Okay, because sometimes it's not. At the slack bus, I don't have PK and QK, right? But I will go around the buses and I will find at every bus. Okay, can I find PK and QK? I will find them if I can, right? And then I go around the system. I identify the types of buses that I have in my system. After I identify the types of buses, I identify the variables that I'm looking for, right? So if it's a slack bus, I know V is a magnitude and angle. I'm looking for PK and QK. If it's a generator bus, I have PK and QK, PK and a voltage as a magnitude, and I'm looking for reactive power and angle. If it's a load bus, I have PK and QK as magnitudes, but I don't have voltage and angle at that specific bus, right? So, and then you construct the bus admittance matrix, right? So you go around your system and construct the Y bus matrix the way we constructed it. And then you sort of, if you don't need to go through all of this, the proof that we went through, but you automatically go to your power flow equations, your P and Q equations. So what do we have at every bus? At every bus, remember, let's say we have a PQ bus. At a PQ bus, do I know P and Q at that specific bus or not? At a load bus, I know the load's active power and reactive power, right? So I know P and Q at the bus. So I know PK and QK. But I don't know voltage as a magnitude and an angle. So I don't know voltage as a magnitude. I don't know VK. I don't know VN. I don't know delta K. Delta K minus delta N is the angle difference between bus K and bus N, right? So this will be later grouped as a theta Kn later, okay? But this is the voltage difference, the angle difference between 2 buses, bus K and bus N. So I don't know the angles, and I don't know the voltage magnitudes. Of course, the impedances, the G's and the B's are known, right? Because we collected all system data. You have to go around, collect all system data. Your cables, you have to collect their data. Your transformers, you collect their data. Transmission lines, you connect loads, you collect it. So you have to collect all the data that you have. So all the G's and the B's, So the admittances, conductance, susceptances, you know. You don't know, for at a PQ bus, you don't know voltage, magnitude, and angle. I know P and Q. So what do you do? What? How can you solve? You don't know voltage. You have two equations and you have no, you have two equations, two unknowns, but these equations are not linear. You have cosines and you have variables that multiply by each other. You have sines and cosines, and you have sines and cosines multiplied by the voltage. So you have unknowns that are not linear multiplied by each other. So it's a nonlinear equation. So even though you have two equations and two unknowns, but they are nonlinear, so there's no way to solve them except using iterations, numerical methods. So the method, you cannot use your calculator merely to do this. Maybe your calculator does numerical, does iterative. I don't think so. I don't think you can use your calculator to solve this. So the way we would do it, and the way that Power World does it, is using a method called Newton-Raphson method. Newton-Raphson is a numerical method that is based on iteration. So what do? We assume certain values for V's and the angles. I assume certain values for voltages and angles, and then I calculate everything on my right-hand side. Right? If I assume voltages and angles, and I know the impedances, then I can calculate a value for my right-hand side at every single bus. Right? And then I compare it to what I know at that bus. Right? If I know PK at that bus, then I compare PK, which I know at that bus, versus my estimate of PK at that specific bus. If they're equal, then what you've chosen, what the answer that the estimate or the guess that you've chosen is correct. Does it make sense? If they're not, then the estimate that you chose was wrong, and you have to find a better estimate, right? And we will find out how to choose a better estimate. Okay, but what is a good estimate to start with, based on what we know from about the per unit system? What is the good estimate to start with for voltages as voltage magnitudes and angles for an unstressed system? Voltage, exactly. So for an unstressed system, voltage magnitudes are all around 1. And voltage and angle differences between buses, again, angle differences are also an unstressed system, meaning there is not a huge amount of power flowing, meaning that the angle differences are also very close. Angle differences are 0. Right? So a good estimate for, and if we are going to have a reference bus that is, for example, going to have an angle of 0, then I can sort of use the absolute angles at the other buses. So if I'm going to measure the voltage angle with respect to a bus having an angle of 0, then every angle at the specific bus is sort of an absolute value as well. So if angle at bus 1 with respect to 0 is angle at bus 1. Angle at bus 2 with respect to 0 is the angle at bus 2. Right? So these angle differences, if we have one of them equal to 0 all the time, meaning the reference, then the angle differences are actually sort of like angles at that specific bus. Yeah. So a good estimate to start with is, as we said, voltage is equal 1, angles equal 0. Right? Plug it into the system and see what you get. Right? And then in an unstressed system, it may be not too far away. If the system is a stressed system, like meaning it's fully loaded, or there's so much reactive power being drawn out that the voltage has dropped considerably, maybe to 0.7 per unit or something like that, or there's a fault somewhere in the system which has dropped the voltage considerably, then your estimate's going to be way off, right? And with the numerical methods, sometimes if your estimate is way off, okay, if you look at simple numerical methods, we're not going to study numerical methods in detail, but simple numerical methods, if your original estimate is way off, then your system will never converge. You will never be able to find a good estimate. You actually keep deviating, right? So I will show you how to find now a better estimate now. But this is the process. This is what we're trying to achieve here. Everybody's okay with this? So let's go back. Instead of, before going and solving a numerical method problem, let's sort of apply what we've done on an example. Okay, so we have a 5-bus system here, and we want to go through and see what we've learned. So input data, so they give you the input data for, so they tell you that you have a 5-bus system and input data are shown in the next tables. Table, and as shown in table 6.1, bus 1 to which a generator is connected is a swing bus, and they tell you, okay, bus 1, use that as your swing bus, swing or slack bus. So what do you know? What do you know about this bus then? I know voltage is a magnitude and an angle. So I know voltage, magnitude, and angle. How about, what is this bus? PQ bus. This is a load bus. Yeah, I just have a load P and Q. How about this bus? It's a generator bus. I have a generator which is 520 megawatts, much higher than my load, right? So then definitely the P is going to be defined by the generator. So I have P defined by the generator, and the voltage defined by the generator, and Q will be defined by the system, right? The Q of 40 megavarts is not really defining the reactive power at the system, unless that is the reactive power limit of that generator, okay? If that is the reactive power limit of the generator, that's a special case, right? That bus will then become a PQ bus, right? Because at that point, because if the load is actually defining the reactive power limit at that bus, then it's a PQ bus, right? But that's a special case in the power flow simulations, right? Where the load is actually defining the reactive power at a generator bus. But for our purposes, I mean, it can happen, but it's a special case. So anyway, so bus 1 is a slack bus. Bus 2 is a load bus. Bus 3 is a generator bus. A generator buses, I know P as a magnitude, and I know V as a magnitude. I don't know Q. I don't know angle. Right? How about bus 4 and bus 5? They are load buses. So if they're not slack buses and they're not generator buses, then they're load buses. Okay? But it's confusing because you don't see an arrow saying there's a load. So actually the load on these is 0. Right? So the load on these two buses is 0. But they are still called load buses. Right? So, but you will define PK and QK at these buses to be 0. Okay? Bus 2, no. Bus 2, it's a load bus as well. It's not a slack bus. So bus 2 is not a slack bus, and it's not a generator bus. Then it's a load bus. So after you define it's a load bus, you figure out what PK and QK are at that bus. If you have specific loads at that bus, then you will have a value for loads, right? And then PK is equal to generator power minus load power. So if it's a load only at that bus, then it's negative. Then PK and QK will be negative at that bus, and that's what they say here. Q2 is equal to 0, which is what's generated at that bus, minus QL2, which is a load QL2, which is 280 megavars. They write it, I mean, it's 2.8. I think they write it in, this is in, they divide it by, I think they use some base power of some value to do this, yeah. Maybe they will show that later, yeah. Maybe they use the 100 megavars as your base, something like 100 MVA as a base, I think. And then Q3, same thing, Q3 is the reactive power, the reactive power at that bus. There's 0 reactive power produced by the generator. And then there is QL3, it's 40 megavar, so it's a minus 40 megavar. Right? But do I really care at Q3? I don't, I mean, it's not very useful. Q3 is actually not something I care about because it's something that I don't even know. Right? This is a PV bus. I only know P and I know V. I cannot use the reactive power equation. So yeah, I forgot to mention something. So we came up with the reactive power equation and reactive power equation at every bus K, right? At a load bus, you can use both equations because you know the reactive power. You have to know the left-hand side to be able to use the equation, right? If you go back to the equation we have, what did we do? I said that what we will do is estimate, give a guess for V and delta, and then compare the right-hand side to what we know on the left-hand side, right? So if I don't know my left-hand side, there's nothing to compare to, right? So at a load bus, I know my left-hand side in both equations, right? Because I know PK and QK. So at a load bus, I can use these two equations at that specific bus. At a slack bus, I don't have anything unknown because I already have my voltage as a magnitude and an angle. So, and I know them specifically. So if I plug in here, I will know what's on the left-hand side without having to guess and estimate and iterate. That's a slack bus. And then at PV bus, I know P, but I don't know Q. So I cannot use the second equation. Can I use the second equation? I cannot. I don't know Q. I don't know. At a PV bus, I don't know P and V as a magnitude. I don't know Q. So I cannot use the second equation. So at a generator bus or a PV bus, I cannot use the second equation. And I don't need to because I already have V. If I know V, I just need to guess one variable, which is the angle, to be able to compare it with the left-hand side, right? So your variables are really not P, Q, and V and delta. These are sort of your unknowns or your states, no, not states, unknowns in the system. But your states of the system, which are what you really need to calculate P and Q, are actually the V's and deltas. Right? Because if you know all the V's and deltas around the system, finish, I don't care, because I can calculate P's and Q's. Right? So does it make sense? Every bus, I can use these two equations. Unless it's a PV bus, I will only be able to use one equation. If it's a slack bus, I don't need any of the equations. Right? And this will, of course, affect the order of the matrix in which I will plug all these equations, right? I will be plugging all these equations in matrices, right? So that's why I said the order of matrices is important, because of the Y-bus matrix, its order is the order of the system nodes. So if it's a three-bus system, it's a 3x3 system, 3x3 matrix, the Y-bus. But the matrices that we will build with these power flow equations, they will depend on the type of buses. The order of the matrix will depend on the type of bus. Right? So let's do some examples and we'll become clear. So yeah, so so the reason I'm saying this is Q3 is not really relevant. I don't really care because it's a PV bus. I mean, this is not really something that I care to. I'm not going to even use it yet. Okay, determine which of the variables Vk, delta k, Pk, and Qk are input data and which are unknown. So I think we went through that. We said that at the slack bus, I know V1 and I know delta 1. So what I need to find out are P and Q. And at bus 5 and bus 4 and bus 2, which are load buses, I know P and Q at the specific buses, and I need V and delta. And at bus 3, I have P and V. It's a PV bus. I need Q and delta. These are the missing variables, right? And then compute the elements of the second row of Y-bus. So the Y-bus matrix, the admittance matrix, just compute one row of the Y-bus matrix. We'll see how to do that. So of course, they give us, again, there's a lot of data that's going to be given, or in your case, you would have to collect as an engineer. And this data is, okay, so here we go and they sort of write all the buses down, the various buses, and write what type of buses they are. And okay, swing bus, we will have it will have a voltage of 1 and an angle of 0. I don't know P and Q at the buses, at the swing bus, and there's no loads at that bus, right? Load buses, bus 2, I know the loads at this bus. So bus 2 is this bus down here. So I know that this is 280 megavars and 800 megawatts. And they use the 100 MVA, as I said, as a base. So that's why this is 8 and 2.8, which are the load powers. And then PV bus, I know the voltage as a magnitude. I don't know the angle. I know the generated power, and I have some load. So I know P at that bus is the difference between the generated power and the load power, right? So Pk at bus 3 or P3 is equal to what? Is equal to 5.2 minus the 0.8, right? P3. And then for buses 4 and 5, they're load buses, but I didn't have, so I don't know voltages and angles, and I didn't really have loads at these buses, so that's why these are all zeros, right? Then then you have to go around and collect data for your system. So you have to look at your transmission lines or cables, and between buses 2 and 4, between buses 2 and 4, between these two buses, I have this line 1 data. So I have to go back and look at what they gave me. So they gave me the R, which you were asking about before. We don't always ignore the resistance. We consider that, but it's very small, right? So they gave me the R, they gave me the X, all in per unit, and then G was 0, and then they gave me the B, which is the susceptance. Remember the equivalent circuit for the transmission line had this JB over 2 on each side. So they gave you B, so you'll have to divide that by 2 when you consider that, because it will be added. It's an admittance connected to a bus, right? So you will add half of it at every single bus, right? So if this was bus 1 and this is bus 2, this is JB over 2, and this is some admittance Y12. So Y11 in the, if you look, this is your admittance matrix. This is Y11, Y12, blah, 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 and Y22, Y33. And then this is, this is symmetric, so Y21 is equal to Y12, etc. This is this is the admittance matrix, right? Structure of the admittance matrix depends on the number of nodes that you have. So Y12, if this is bus 1 and bus 2, Y12 is equal to what? The negative of all the admittances connected between bus 1 and bus 2. So it's Y12. Bus 1 and bus 2 have what between them? This one. So it's the negative of this is what you plug in here. Right? How about Y11? Y11 is equal to the sum of all admittances connected to bus 1. So bus 1 is here. This is admittance connected to bus 1. This is an admittance connected to bus 1. So you add JB over 2 plus this admittance. And they gave you B for the transmission line. So you will take half of it. JB over 2 will be added at one bus. At bus 2, Y22 will consider the other half of this. Right? So they gave you, so they went and looked at all their cables, and they have all the parameters, so the pi equivalent circuits for the transmission line or cables that they have. They have those. And then they looked at their transformers. They have two transformers in the circuit, one T1 and T2 here. These transformers, they only considered the series branch. They did not consider the shunt branches, the G and JB, which we will typically ignore. So they gave you those as 0, and then they considered the series branches only and ignore phase shift. So we only have a series impedance between buses 1 and bus 5, just an impedance, right? So now you have all your everything you have. You have all the admittances between buses you have based on your knowledge from the transformer, knowledge of the transmission lines, right? So now you can start constructing your system, right? So you go through your buses. Okay, at bus 1, it's a slack bus. I know that for a slack bus, we generally will start with a 1 and 0, okay? But this is not necessarily the case all the time. Let's say if you have a loaded system, and in Power World, sometimes it will not converge, actually. Sometimes if your system is very loaded in Power World will not converge. Have you tried that? Try maybe build a small system or pull up one of the examples and increase the loads. Okay, increase the loads, or if there's a limit, remove the limit and keep increasing the loads. It will tell you it will not converge. Right? So a way to solve this would be to do the following: to reduce the loads. If you have a loaded system, reduce the loads, right? And then start with the guesses. The guesses would be, we call one voltage magnitudes of being 1 and angles of 0. We call this a flat start, right? We call it a flat start, because it's, for an unstressed system, it's a good selection to start with, right? So we call this the flat start of the system. And then, if the system converges, keep increasing the load slowly. If it converges, use the numbers that you have at the specific buses. Now because you remember, we have PK and QK equations at every single bus. So you have to get estimates of all the voltages and angles in your system to be able to start. right? So you initially said, okay, I will have all voltages as 1 and all angles being 0. And it did not converge when the load is very high. But when you decrease the load, it converges. So how about doing, increasing the load slowly, and then every time, keep increasing the load until it stops convergence. When it stops convergence, decrease it a little bit, and then the previous step where it converged, take these numbers and use them as your start. Right? Because again, these numerical methods, if you choose a very far away guess to start with, it will not converge. Yes, ma'am.
So for wire and the one angle zero, that will be changing up until it stops converging, and then hit the last one.
Yeah, if it doesn't converge, for some reason it doesn't converge, that's what I would do, right? Again, this is just from a practical perspective. This is not. I mean, for our cases, we will always have slack bus 1 and 0. We will always assume our angles will start with 0 and our voltages will start with 1, right? But practically, if you have a system that is stressed and you want to do a power flow analysis for that system, this is what you would do in that case, right? You would not start with because it's a guess, right? I mean, it's a guess. If the guess is bad, it will not converge. Okay, what, you sit down and wait? So you have to find a way to solve it, right? So that means your guess is bad, so you have to find a way to find a better guess, and that's a way to find a better guess, right? Anyway, so now we go back to the steps of the problem. So we understand the givens, we understand the system, and we understand all the data that they gave us. And now we sort of have to go back and go through the process that we have, and go through our buses and identify what the buses are. We did that for the various buses. Right? And we identified the unknowns that we have at every bus. So now all of these are unknowns that we have in the system, and these are known variables. All of this is just part of the construction process, right? And then they told us also what? They told us to compute the elements of the second row of Y bus. So remember, Y bus looked like Y bus looked like this, right? Y11, Y12, Y13, Y14, until Y1n, right? All the way until Y1n. And this is Y21, Y31, Y41, blah, 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 all the way until bus n, right? And this is an n by n matrix, depending on the number of nodes that you have in your system. So they're asking you to calculate the second row of this admittance matrix. They're not asking for the full admittance matrix, just the second row. So this is it's a 5 by 5 system, right? So we expect to have a bus admittance matrix Y bus as 5 by 5, right? So they're asking us to calculate Y21, Y22, Y23, Y24, and Y25, right? That's what they're asking, the second row of the bus admittance matrix. So let's go back to our system. Our system here is bus 2 connected. Okay, bus 2 is connected to bus 4, right? And the connection between them is line 1. And they gave us the impedances and admittances for bus 1, for line 1, right? Mm-hmm. How about bus 2? Is it connected to bus 3? It's not connected to bus 3. So the impedance is 0, the admittance, so there's no admittance between them. The admittance in this case between them is 0. Right? So they're not, yes ma'am.
What about bus 1?
Same thing. So Y21 will be 0. Y23 will be 0. Right? It's only the admittance between the two specific buses that you have. So Y21 will be 0. Y22 will exist. So only Y25 and Y24 will exist. Everything else is 0. So Y22 will exist. Y25 will exist. And Y24 will exist. 21 is 0. And 23 is 0. Okay? So 21 is 0. 23 is 0. 24 will exist. And 25 will exist. Right? 22 is equal to what? Y22. What? the sum of all the admittances connected to bus 2. So we go to bus 2 and see, bus 2, I have this admittance of line 2. And I have also what? Remember, this is a transmission line. It has a shunt branch, shunt susceptance. So I have to consider the JB over 2. Right? So I have, remember, I have a here I have this admittance, and I have a shunt branch here equal JB over 2. They gave me B for line 2.5. They gave me that. So I have to consider this, I have to consider that, and I have to consider this as well, right? Because Y22 is this plus this plus this. Okay? There is, sorry, I should, good. JB over 2 here for this line as well. Good point. Half a point, that's fine.
Do you consider those as parallel, or how do you add them?
No, you just add. You add all admittances connected to that line, to the bus. So Y22 will be this admittance plus this admittance plus this admittance plus this admittance. So there will be 4 admittances for Y22. And then for Y24, it will be the negative of this one. Right? Y24 will be the negative of this admittance. And Y25 will be the negative of this admittance. Right? So now I have the 3. Okay? So I have 3, and I found what the 3 are. And they're all based on, of course, the data from the table. So this is Y22. This is another typo. Okay? Because remember, this is I have the JB over 2 for the 2.4, the JB over 2 for the 2.5, and then the 2 admittances. Right? And then for the Y24, Y25, it's just the negative of the admittance between these two, between bus 2 and bus 4. And this is the negative of the admittance between bus 2 and bus 5. Right? So I found all of them. Right? So all of this is still, we still did not do the start the power flow problem. We're still setting it up. So any questions on the elements of the admittance matrix? No? Still setting up the power flow problem. Yeah. Next we will, next class we will, okay, apply. Now we've set up everything. Okay, now I need to construct, at every bus, I go and, okay, I have, it's a load bus, so I can use my P and Q equations. So I have 2 equations. Another load bus, 2 more equations. Another load bus, another 2 equations. PV bus, 1 equation, because I don't have Q. A slack bus, no equations, right? Now we'll construct a matrix of all these power flow equations. And then solve them. And then compare the power flow equation left-hand side and right-hand side together. And then find a way to find a better estimate. Okay, so that's the flow. So next time we will do this. Hopefully today we set up the problem properly and you understand the motivation.